my report on Bose-Einstein condensation of magnons in nanoscale devices. The studies I will present today were carried out in recent years at the Department of Physics of the University of Kaiserslautern-Landau in the research group Magnetism led by Burkhard Hillebrands. Currently, our research on the fundamental properties of magnon condensates and the possibilities of their application is funded by German Research Foundation within the framework of the Transregional Collaborative Research Center SPIN+X, Spin in its collective environment, and by the State Research Center Optimus. The results were obtained in collaboration with our colleagues from Austria and the USA. More than 24 co-authors contributed to these results. I don't have the opportunity to list them all. However, I would especially like to acknowledge the contribution of Michael Schneider and David Breitbach, who directly carried out a huge amount of experimental work started by a former member of our group and now a professor at the University of Vienna, Andriy Chumak. The understanding of the physics of the discovered phenomena would not have been possible without the theoretical support of Vasil Tiberkevich and Andrei Slavin from the University of Auckland. And of course, our research would not have been possible without nanometer-thick yttrium-ion garnet films grown by Karsten Dubs at the Industrial Research Institute Innovent in Jena. Before we turn directly to magnetic phenomena, let us recall what is the Bose-Einstein condensation, which was predicted by Albert Einstein back in 1925 for an ideal gas of bosons, particles described by a quantum mechanical statistical distribution derived by Satyendra Bose at that time. At high temperatures, an ideal gas behaves as an ensemble of independent particles moving with different thermal velocities. With a decrease in temperature, and hence in the impulses of these particles, the wave properties of matter begin to appear and the de Broglie wavelength increases. After reaching a certain critical temperature, the wave function of macroscopic number of particles mature into one, and the new object, the Bose-Einstein condensate, appears at the lowest energy level of the system. For the case of an ideal gas, it means that the corresponding molecules simply stop. As you can imagine, this looks very unusual from a classical point of view, given that potentially these particles could move at any speed slightly different from zero. Also, as early as 1938, Fritz London suggested that the Bose-Einstein condensate underlies such fascinating phenomena as superfluidity and superconductivity. Bose-Einstein condensates of real particles were first obtained only in 1995 in dilute atomic vapors at ultra-low temperatures. The temperature was 170 nanokelvins. Just 6 years later, the leaders of two successful research teams were awarded the Nobel Prize. Sometimes, along with solids, liquid, gases, and plasmas, the Bose-Einstein condensate is referred to as the fifth aggregate state of matter. And as Wolfgang Ketterle said, it is the coldest matter in the universe. But would it be possible to get such a condensate at higher temperatures? It seems that there is no fundamental obstacles for this. As the density of particles increases, the critical temperature of condensation also increases. In fact, Einstein himself said, "But what happens now if I let the density of the substance grow even more at this temperature? I claim that in this case a number of molecules, which grows with the total density, transfers into the first quantum state without kinetic energy. However, a significant increase in temperature is not possible for an atomic gas. An increase in density will increase the interaction of particles and will eventually put such a gas into different aggregate state." At the same time, it turned out that Bose-Einstein condensation at much higher temperatures is possible for a gas of a weakly interacting quasi-particles, quanta of collective excitations, which are also bosons. Moreover, Since the number of quasiparticles is not conserved and decreases with cooling of a medium, artificial increase of the quasiparticle density is practically the only way to realize their condensation. And such condensation has been realized for photons, exciton polaritons, and magnons. I should proudly note that the experimental work on magnon condensation was initiated by my scientific father, professor of the radiophysical department of Taras Shevchenko Kyiv National University, Gennady Andreevich Milkov, and successfully achieved in collaboration between our group and the group of Sergei Demokritov from the University of Münster, still in 2006. Being a macroscopic quantum phenomenon, Bose-Einstein condensation of quasiparticles result in spontaneous coherence in a quasi-equilibrium wave system, can lead to effects similar to superconductivity and superfluidity, can be used in quantum simulations of cosmic events, and is potential candidate for application in quantum calculations. Some of such properties of the magnon condensate have already been observed and even utilized. These are monochromatic microwave radiation from the system of strongly excited magnons, supercurrent in a room temperature Bose-Einstein magnon condensate, magnon-Josephson oscillations, and recently proposed by us classical analog of qubit logic based on a magnon Bose-Einstein condensate. Let us move closer to the magnon condensates. Wave-particle duality is the concept in quantum mechanics that every particle or quantum entity may be described as either a particle or a wave. Magnons, quanta of spin waves, and no exception for this rule, then can be characterized by energy, momentum, mass, and spin. Moreover, they participate in weak interaction leading to their scattering over the spectrum. Magnons are bosons with spin equals 1 and similar to other quasiparticles are described in thermal equilibrium by Bose-Einstein distribution with zero chemical potential map. An example of such a distribution at some temperature T you can see here. However, external injection of magnons beyond the thermal equilibrium level increases the chemical potential to the bottom of magnon spectrum, omega minimum here, and leads to Bose-Einstein condensation scenario even at room temperature, as shown schematically by green line here. What is the magnon Bose-Einstein condensate? BEC of magnons is a coherent spin wave formed spontaneously from the chaotic magnetization motion in a quasi-equilibrium magnon system. In all our experiments, magnon condensate studies are performed using deuterium-ion garnet because this material has the lowest magnon damping in nature. On the right, you see the dispersion curve of magnons propagating along the direction of stationary magnetization in tangentially magnetized Ig film of micron thickness. This is the lowest mode in the magnon spectrum. As a consequence of a competition between dipole and exchange interactions, it has two minima, here and here, whose frequency depends on the applied external magnetic field. The standard approach for creating a high-temperature magnon condensate, known since the discovery of this phenomenon, is microwave parametric pumping, when the alternating magnetic field HP is oriented along the magnetization field H. In this process, microwave photons of the pumping field split into two magnons of half frequency with oppositely directed wave vectors. In contrast to ferromagnetic resonance, the density of parametric magnons is limited not by their attenuation, but by nonlinear process, and therefore can reach much larger values. The thermalization of pumped magnons due to the four-magnon scattering process creates a quasi-equilibrium region of overpopulated magnon gas near the bottom of the spin wave spectrum. When a certain threshold density is reached, the magnon density at the bottom of the spin wave spectrum increases sharply, and a coherent state, Bose-Einstein condensate, is formed in both minima. The described technique is quite versatile. It can be applied to both bulk examples and films with thicknesses ranging from tens micrometers to tens of nanometers. Moreover, our recent study shows that it is possible to change the magnetization geometry and by magnetizing the films perpendicular to its plane to condense magnons in the Kittel mode of uniform precession. The monochromatic electromagnetic radiation of this mode can be detected using simple microstrip or loop inductive antennas. However, it can be critically noted that also the coherent magnon condensate arises spontaneously in the thermalized gas of injected magnons. The injection itself requires an external, powerful source of coherent microwave radiation. Is it possible to obtain a magnon condensate without using microwave pumping? Is it possible, for example, to utilize thermal energy for this process? Our answer is yes. For this purpose, it is necessary to apply our proposed concept of rapid cooling. The main ideas behind rapid cooling is rapid decrease in phonon temperature and the generation of excess magnons due to the imbalance between phonon and magnon temperatures. To achieve this, we need to manipulate the temperature T in the Bose-Einstein distribution quickly enough. On the right, the black line shows the distribution of magnon density versus frequency at some initial temperature T1. Let this be room temperature. Since the magnetic sample is in thermodynamical equilibrium, the magnon temperature has the same value and the magnon chemical potential is zero. If we slowly heat our sample to a temperature T2, the number of magnons as shown by the red curve will increase, but the system will remain in thermodynamical equilibrium and its chemical potential will not change. What happens when the magnet sample cools down? It depends on how fast the cooling takes place. For the concept of rapid cooling, it is critical that the cooling rate of the crystal lattice significantly exceeds the relaxation rate of low energy magnons. Suppose that the phonon temperature decreases to the initial level instantaneously after the heating is stopped. Then we have an excess of magnons with respect to the temperature of lattice. Because the relaxation of magnons into the phonon reservoir, their density decreases. At the same time, due to the process of Fogg-magnon and Cherenkov scattering, which preserves the number of magnons, there is a redistribution of thermal magnons to the region of low energies. In this process, the chemical potential of the magnon gas increases, and if it reaches the bottom of the magnon spectrum, Bose-Einstein condensation occurs. However, instantaneous cooling is an idealization. How can we achieve sufficiently fast cooling in practice? The answer is by using microscaled samples. That means we have to use nanometer thick ink films. Here you can see our experimental setup. It is two contacts, and between them is placed 70 nanometers thick yttrium ion film, as long as 4 micrometers and width of 100 nanometers. And this film is covered by platinum layer of 7 nanometers thick, deposited via MBE and connected to the gold electrodes. In order to heat our sample, we apply DC electric current pulse and to these electrodes, and current flows through the platinum and heats it up. And due to the Joule heating, the temperature increase in our experiment was up to 150 Kelvin above the room temperature. Here you see the measurement of the increase in temperature due to the change of resistivity of our platinum, and also the simulation performed by COMSOL. And you see the temperature increases and after that decreases on 10th nanosecond scale. How we will detect appearance of our Bose condensation and distribution of magnons? For magnon detection, we use time and space resolved brilliant light scattering spectroscopy, when magnons are created or annihilated in interaction with probing light, here this light, and after that Stokes and anti-Stokes component in the scattered light spectrum and analyzed using Fabry-Perot interferometer. We have used in our experiment a few samples, and here you see the configuration of experiment when our yttrium ion garnet film is magnetized by magnetic field 188 millitesla along the longitudinal axis of this sample and along of the current which flows through this. And here you can see the spectrum obtained by BLS of fundamental mode, its thermal spectrum at lattice temperature 300 Kelvin, and the fundamental mode and the first standing thickness mode here. And in some moment we apply the current pulse to our platinum cover, and temperature of the yttrium ion garnet films will increase. And here the increase up to 420 kelvins. In this process we see two effects. The first, frequency drops down of our modes, and the second one, the intensity also decreases. Frequency drops down due to the reduction of magnetization due to the heating, and reduction of magnetization also lead to the decrease in efficiency of brilliant light scattering detection. But what occurs if we will switch our heating current pulse off? In this moment, we see a very interesting situation. When for the high first standing wave mode, we see only the restoration to the previous frequency and intensity, and completely different process develops in the fundamental, the lowest frequency mode. We see the concentration of magnons in this mode and interpret it as Bose-Einstein condensation. In order to check this, we performed the measurements of the chemical potential, comparing the relative occupation of the fundamental mode and first standing thickness mode, and using the Rayleigh-Jeans distribution is valid for low energies. And here chemical potential is indicated by red experimental dots. And you see that in some moment after the heating pulse is switched off, chemical potential increases, reaches the bottom frequency of fundamental mode, and our Bose-Einstein condensation occurs. If we have a thin magnetic film coated with a heavy non-magnetic metal, can we use spintronic effects such as the spin Hall and spin torque effects to influence the condensation process? Yes, it is possible. Injection or annihilation of magnons during the DC pulse application can change the threshold of rapid cooling induced BC formation. In our next experiment, we use the same configuration as previously, only our film was magnetized perpendicularly to the direction of electric current, what allows of spin current formed due to the spin-dependent scattering of electrons in platinum propagate from platinum into yttrium ion film. And also thickness of yttrium ion garnet film was decreased, and quality of platinum pad was increased in such case to ensure better efficiency of spintronic spin torque processes. It is indicated here. So we increase spin transfer torque and increase spin Hall angle. We have used three different magnetization configurations. In one magnetization configuration, magnon injection was possible. In another, magnon annihilation, when we change the direction of the current and change the direction of spin current. And also, when we magnetized our sample along the magnetization direction, no spin orbital top contribution was expected. And in such case, what we can see, it is the first. For no spin orbital contribution, we have no influence on of spintronic effects on Bose-Einstein condensation caused by rapid cooling. In case of magnon annihilation, we can completely suppress the Bose-Einstein condensation. And in case of magnon injection, we can enhance this process. And here the enhanced Bose-Einstein condensation. So we can say that using the spintronic effects, we can control Bose-Einstein condensation efficiently. And I should say that rapid cooling, it's not only fundamental phenomena, it can be used for practical purposes, for example, as an amplification mechanism. We improved our experimental setup by adding the microstrip antenna in order to excite externally propagating spin waves in our yttrium ion garnet field. And what we can see, if our microwave, if we will apply only DC pulse only, we see no change in thermal spectrum at some distance from the area where heating occurs. Here focal spot, probing spot on distance delta X from the area of heating. It is the black curve. When we will apply spin wave packet, we observe here the propagating, the signal of BLS caused by propagating magnons. It is the red pulse here. And if we will apply spin wave plus DC pulse, and DC pulse is applied such that spin waves propagate through the heating area in the moment when it starts to cool down. In such case, we see the increase in the intensity of propagating spin waves, and thus we can say that we can realize Bose-Einstein condensation based amplification mechanism. Here you can see that this amplification depends on the overlap of heating and microwave pulses. It is clear because if pulse propagates in the moment when we apply heating, we only create the area of additional scattering for propagating spin waves in the area of reduced magnetization. Amplification occurs in the case of cooling. And okay, I am going to summary. I can say that rapid cooling induced magnon Bose-Einstein condensation demonstrate new paradigm, non-equilibrium of magnon and phonon system using for initiating this process. Condensate forms from completely incoherent thermal magnons, and we harvesting thermal energy. Bose-Einstein condensation occurs on the nanoscale and is electrically pulse driven. We can realize control of the magnon Bose-Einstein condensation by the spin Hall effect. Additional magnon injection or annihilation decreases or increases the threshold of condensation. The rapid cooling effect works as an amplification mechanism. Magnon redistribution to initially highly occupied states occurs, and we have some artificial attraction of thermal magnons to coherent spin waves. And amplification of externally excited spin waves occurs due to the scattering to this state of incoherent thermal magnons. Thank you for your attention.